Recurrence relations. Let's consider the following sequence of integrals. The integral from 0 to pi on 2 of sine x dx, the integral from 0 to pi on 2 of sine squared x dx, the integral from 0 to pi on 2 of sine cubed x dx, and the integral from 0 to pi on 2 of sine to the n of x dx. Should be an n. And we're going to let this last one equal I n. And it can actually be shown that I n is actually equal to n minus 1 on n times I of n minus 2. And the reason this can be helpful is we can actually find, once we know one integral, we can use it to find all the others. So for example, we could easily find this integral over here, I1, because if we did that, I1, so let's call this one I1, we know that the integral of sine is minus cos from 0 to pi on 2. Evaluating this, we get minus cos of pi on 2 minus cos of 0, and cos of pi on 2 is 0, so we just get 0 minus minus, which is plus, cos 0 is 1, and we get 1. So knowing that I1 is equal to 1, we could easily find I3, for example. So we could find this integral here of sine cubed x without doing any integration, because we'd know that I3 is equal to 3 minus 1 on 3 times I1, and we get 3 minus 1, which is 2 on 3 times I1, which we know is 1, and this would evaluate to 2 on 3. So we get that answer really quickly without actually doing any more integration. And how do we actually get these recurrence relations? Well, let's do an example now on how we can actually get those, the reduction formula. And this reduction formula is specific to this case, and each of these integrals are going to have their own reduction formula, as we're going to see with more examples. Let's have a look at this example here. In equals the integral from 0 to pi on 4 of tan of x to the power of n dx. How can we go ahead and get the reduction formula here? So now we're going to rewrite this integral as the integral from 0 to pi on 4 of tan of x to the n minus 2 multiplied by tan squared x. Because we're multiplying by the same base, we add the powers together and we get back to tan of x to the n. Now, integral from 0 to pi on 4 of tan of n minus 2 of x times tan squared is the same thing as sec squared minus 1. Should be a dx here and here. And let's go ahead and expand this out. So we get the integral from 0 to pi on 4 tan of x to the n minus 2 times sec squared x minus tan of the n minus 2 of x, all the dx. Now remember that we let in equal tan of x to the n. So tan of x to the n minus 2 is just going to be I of n minus 2. So this part over here is just going to be I of n minus 2. And I of n is after the integral has been evaluated. So we don't have to integrate I of the n minus 2. That's the integral evaluated equals I of the n minus 2. Now over here, we have a reverse chain rule situation where we have tan being multiplied by its derivative. So what we can do to find this integral, let's just write it out first. Tan of n minus 2 of sec squared dx, sec squared x dx. So since we have this reverse chain rule situation, we can all write this as the integral. So we just add 1 to the power. So it's adding 1 to n minus 2 is going to give us n minus 1 of x, all over that new power, n minus 1, from 0 to pi on 4. Minus I of n minus 2. Now we can go ahead and sub in those values for x. So we're going to get tan of pi on 4 to the n minus 1 over n minus 1 minus tan 0 to the n minus 1 over n minus 1 minus I of n minus 2. Remember, this all equals in. Tan of pi on 4 is just 1, and 1 to the n minus 1 is just 1. So you get 1 on n minus 1 minus tan 0 is 0, and 0 to the n minus 1 is just 0, so it's all going to be 0, minus I of n minus 2. So we get our final answer, in equals 1 on n minus 1 minus I of n minus 2 for our reduction formula. Let's have a look at another example. Let's look at in, integral of 1 to e of ln x all to the n dx. So here we're going to need to use integration by parts to get the reduction formula here. So we're going to let u equal ln x to the n and dv equal dx. So we're going to have u equals ln x all to the n and dv equal to dx. So we'll have du dx equals n to bring the power to the front, ln x, subtract 1 from the power, and times by the derivative of what's inside, so we get 1 on x, and the integral of dv is v, and the integral of dx is just x. So now we can go ahead and rewrite this integral as u times v, so we get x times ln of x to the n, minus the integral from 1 to e, so this was evaluated 1 to e, integral of 1 to e of v du, so we get x so du, we can write that as n over x, just tidy this up, ln x to the n minus 1 dx. So all that's going in for du, so times in this by n over x ln x to the n minus 1 dx. The x's will cancel out here. So we get x times ln of x to the n from 1 to e minus the n can come to the front. We get the integral of 1 to e of ln x to the n minus 1 dx. Now, looking back at our original definition, in was equal to the integral from 1 to e of ln x to the n. So the integral from 1 to e of ln x to the n minus 1, that's just going to equal in minus 1. So we've got x ln x all to the n from 1 to e minus n times I of n minus 1. And we can go ahead and sub in our values of e and 1. So subbing in e for x, we're just going to get e times ln e to the n minus subbing in 1, we're going to get 1 times ln 1 all to the n minus n times I of n minus 1. ln e is just 1 and 1 to the n is 1, so we're just left with e, and ln 1 is 0, so that's all gone. So we've just got e there, minus n I of n minus 1. So we just get e minus n of I n minus 1. So have a look at one more example. So let's say we have I equals the integral of e to the x times sine x dx. So here we want to use integration by parts. And we actually want to let u equal to sine x and dv equal to e to the x dx. So du dx is just going to be cos x, and v is going to be the integral here, which is just going to be e to the x. So now this is going to equal u times v, so we're just going to get e to the x times sine x minus the integral of v du. So we know du is equal to cos x dx. So we get e to the x times cos x dx. Almost looking like what we started with in here. So it looks like we're going to need to go again. So we're going to do another integration by parts. So here we're going to let u equal to cos x and dv equal to e to the x dx. So du dx is going to be minus sine x. V is going to equal to e to the x. So now we're going to get the bit out the front, the e to the x sine x, minus now all of this is u times v. So we're going to get e to the x cos x minus the integral of v du. So we're going to get e to the x times minus sine x dx. You can tidy this up a little bit. E to the x times sine x minus e to the x cos x. Here we're going to take the minus out the front, so this will become plus. Integral of e to the x sine x dx. And now, if you look closely, integral of e to the x sine x dx is actually what we started with, and that all equals I. So what's happening here is we're getting a recurrence of the integral, which means we can just sub in I for that integral, because we defined that in the beginning as I. So we get minus e to the x cos x plus I. That was what we started with. We can tidy this up. So you get I equals e to the x sine x, expanded out, minus e to the x cos x minus I. Take the I to the other side, so we get 2i equals e to the x. You can even factorize out the e to the x and get sine x minus cos x, and divide both sides by 2. So you get I equals a half e to the x of sine x minus cos x as our final answer to evaluate the integral. And can't forget to plus the constant on the end.